Okay, it's recording.
Yep, that looks good. Are you there, Luigi?
I'm here.
Great. Okay, it's great. So it's a great pleasure to have Louigi Addario-Berry as our first speaker, and he's going to talk about height bounds for random trees. And if you have questions and you want to put them in the chat, then I'll try and keep an eye on the chat and let Luigi know if I see anything, if that's okay with you, Luigi.
Thanks very much. Yeah, and I'll try to keep an eye on the chat as well.
Okay, great. Thank you.
Great. So thanks so much for the invitation. It's a pleasure to see you all, or to see some of you on the 6 people that that Zoom has randomly selected for me. I'll scroll down and look at some more of you at the end of the talk. I just waited until the last minute because people were still filtering in. I'm going to put a link to the slides in the chat. I'll just grab that. I wanted to say right off the bat, I was having some connectivity issues earlier, so if my signal's bad, let me know and I'll tether to my phone. Right now it seems okay. And there's a link to my slides for anyone who wants to follow along. But I'm going to be writing down as though I didn't pre-prepare slides because I want to pace myself. So so you don't have to worry. It's going to go at the speed you see there. Right. So so I'm going to start by telling you a few theorems about random trees, and then I'm just going to tell you the sort of 2 main tools we use to prove those theorems, and leave it at that. Once you have the tools, the proofs are fairly natural. Before we had the tools, I mean, I've been thinking about this sort of problems for quite some time, and until we found these new tools, we really just weren't ready to prove the results. But now we have the tools, we are. So so I'm going to define what I'll call a combinatorial tree. That's not a particularly universal term. It's just a term for this lecture. So by that, I'm going to mean a rooted labeled tree. With vertices BT and edges ET. And I'll always assume that the vertex set for such a tree is so the vertices are labeled by some finite set of positive integers. So square brackets n for the first n integers, and then I'll write that the size of the tree is the number of vertices is n. Okay, so then for a vertex of such a tree, I'll write C of V, or CT of V, for the number of children of the vertex V in the tree T. Okay, and then the child sequence of the tree is just the list of numbers of children of all the vertices of the tree. Okay, so that's because the vertices are just labeled by 1 up to n. This list I could write as CT1 up to CTn, where n is the size of the tree. Okay, and then so that's what I mean by so this defines a combinatorial tree. This is just some notation about combinatorial trees, and then so I want to define a set of combinatorial trees. So this is the set of trees with a given child sequence. So so if I'm given non-negative integers C1 up to Cn, then I'll write so script T sub C for the set of combinatorial trees that have size n and CT, so the child sequence equal to this particular sequence C. Okay, and here this quantity n should be 1 1 plus, so the sum of, well, okay, so I'm implicitly here saying that, no, so n is the length of the sequence. That's fine. So this definition works, except that, so for there to be a tree with a given, where the vertices are 1 up to n, and vertex I has ci children, it had better be the case that the sort of the sum of all the degrees is correct. So this set of combinatorial trees with a given child sequence will only be non-empty if the sum of cu for u of vertex for u from 1 to n is equal to n minus 1. Okay, and that's just because in any tree, if each vertex sums its number of children, then you're summing all of the edges of the tree, which is 1 fewer than the number of vertices. Okay, so so that's what a combinatorial tree is. And just to give you a quick example, so let's look at a sequence C1 up to C6, and so let's say it's 2, 0, 0, 3, 0, 0. So that says vertex 1 has 2 children, vertex 2 has 3 children, and all the other vertices are leaves. Okay, so in that case, the set TC has sort of just 2 possible shapes. Vertex 1 could be the root, and vertex 4 its child, or vertex 4 could be the root, and vertex 1 its child. And in the first case, there's 4 possible labelings. I just have to choose which of the labels 2, 3, 5, and 6 is a child of 1. And in the second case, there's 4 choose 2, 6 possible labelings. So the set TC in that case has size 10. Okay. And now a random combinatorial tree is just, so this is a definition. So this is a random tree T, which is uniformly distributed over TC for some child sequence C. Okay, so it's a very simple natural definition. Nice thing about combinatorial trees, they sort of specialize lots of natural classes of trees, like the family trees of branching processes, BNMA trees, or simply generated trees. There's many trees, many other models of random trees where you can deduce results about those trees from results about random combinatorial trees by averaging out. So if you can prove results about random combinatorial trees, you can often then transfer those to very well-studied models of trees. Okay, so here's our first main theorem then. So this is joint with Serta Donderwinkel, doctoral student with Christina Goldschmidt in Oxford. So we prove that, so for any, the theorem, our results are mostly about the heights of random trees. So this theorem is a tail-bound for the height of a random combinatorial tree. It says that, so for any epsilon, there exist positive constants little a and big A, such that the following holds. So if I take any random combinatorial tree, with some size n, okay, and the parameter epsilon comes in because I want to insist that it has at least epsilon n leaves. Okay. Then for any x greater than 1, the probability that this tree, this random combinatorial tree, has height at least x root n is at most a e to the minus little a x squared. Okay, so this is a uniform sub-Gaussian tail-bound over all all trees with at least a epsilon proportion of the vertices being leaves. So there's a question in the chat. Oh, sorry, that should say that there's two questions in the chat. I'll address the second one first. Here, this should say the height of the tree and not the size of the tree. So the height of the tree is just the greatest graph distance of any node from the root. Okay, so these trees both have height 2 here. And then the first question was the definition of the law of T depends on C. That's right. So I'm saying this tree is, so this bound holds uniformly over any law which is a uniform sample from some combinatorial tree. Okay. So the role of this epsilon here is worth mentioning. A tree, one possibility for a combinatorial tree would be a tree where every node had exactly one child, except for one node which was a leaf. And then the only possible tree topology that you would see is a long skinny path, which would have height n-1. Okay, so this is a sort of pathology that happens if there's too few leaves, if there's too, or sort of equivalently, if there's too many path vertices. Okay, but once you rule that out, you get uniform sub-Gaussian tailbands. And it's, so in fact, we can say something, I won't belabor this, but we can be a bit more precise here. So we can get some more explicit dependence of the constants on one another, but that's a sort of secondary point. I also wanted to mention at this point that so these are the sorts of bounds that you'd see for the height of a continuum random tree if you are familiar with that object. So this is somehow saying that bounds that are well known to hold for, say, bien-aimé trees, conditioned branching processes with finite variance offspring, or for Brownian continuum random trees, in fact, are not a feature of any kind of convergence in distribution or very special characteristics of the model. They really hold quite universally. So that's the first point. And now I'd like to get to the second point, which relates to this in a way relates to this condition on epsilon, on how many leaves there are, how many path vertices there are. So that's our second set of results. I see another question in the chat. So the fact that there's a proportion epsilon of leaves is a property of C. Yes, that's right. So here, right, there's two-thirds of the vertices are leaves. So the condition is indeed on the number of zeros in the child sequence. Okay. Following on that, I used the phrase path vertex a second ago, and so I want to define that because it's going to come into the next theorem. So a path vertex is a vertex with exactly one child. Okay, so a leaf has no children, a path vertex has exactly one child. And now I'm going to define a special class of trees. So for if you give me numbers L, which is at least 1, and P, which is at least 0, I'll let BLP be the set of all sub-binary combinatorial trees with L leaves and P path vertices. Okay, so that sub-binary means every vertex has either 0, 1, or 2 children. So in fact, here I'm telling you exactly how many nodes with 0 children, that's L. Nodes with 1 children, that's P. And in fact, this immediately implies that then there's also L-1 nodes or vertices with exactly 2 children. Okay, so just to make sure the definition is perfectly clear, I'll give you an example here. So the class B31 So this means there's 3 leaves and 1 path vertex. So there's 3 possible topologies. There's this topology, and there's this topology, and there's this topology. You can see in each case there's 3 leaves, 1 path vertex, and then therefore 2 vertices of degree 2. Okay, and so for each of these, there's 6 factorial possible labelings. Okay, so the size of this class, this set here is 720 times 3. Okay, so then our second theorem, also with Surte-Donderwinkel, says that if T is any random combinatorial tree with L leaves and P path vertices, then I can compare its height to a uniformly random tree with L, sub-binary tree with L leaves and P path vertices. And there's a stochastic relation. So then the height of T is stochastically at most the height of B. Okay, so this says that among all trees with a given number of leaves and a given number of path vertices, the sub-binary ones are the tallest. Okay, so this sort of this is formalizing a heuristic that has been in the back of my mind for a long time, which is that sort of large degrees make short, bushy trees, right? If you have the 2 extreme trees, if I tell you I want a tree with 100 vertices, there's the 2 extreme things you can do to maximize or minimize the height are either 1, you just make a long string of height 99, or on the other end, you make a single vertex of degree 99, and then all of its children are leaves. Okay, so those are the sort of extreme examples of the heuristic, that large degrees make short trees, small degrees make tall trees, and this theorem is sort of a quite precise formalization of a stochastic relation on the height. Okay. So in fact, there's something stronger you can say, which is that, so this is the last theorem, and then I'm just going to finish by showing you an animation of the proof technique. So if I take a child sequence, C1 up to Cn, and I so what I'm going to do is look at what happens when I sample either a random combinatorial tree with this child sequence or a random combinatorial tree with a different child sequence. So how am I going to form the different one? So I start from this one, C1, and I'm going to change 2 of the entries, Ci and Cj, in some way. So I'm going to increase one of them by 1 and decrease the other by 1, so that I still have a valid child sequence at the end. Okay, and I'll do that just by subtracting 1 from one entry and adding 1 to the other entry. Okay, so I'm taking 2 of the degrees, I'm making 1 smaller and 1 bigger. So here, in terms of the picture of 2 trees, you can imagine just taking a branch that was attached to vertex I and sort of shifting it over to vertex j. That would reduce the degree of I by 1 and increase the degree of j by 1. Okay, and the last theorem I want to tell you about says that if that makes the degrees more even, if it smooths them out, then it makes the height lower stochastically. And if it makes the degrees more biased, if it creates large degrees, then that decreases the height stochastically. Okay, so the theorem is that so if Ci is bigger than Cj, which is non-zero, so in this case, I'm evening out the degrees, right? Because I'm moving a degree from a bigger vertex to a smaller vertex. And so T is a random tree from the class TC, and T prime is a random tree from the class TC prime. Then this evening out stochastically reduces the height. So the height of, or stochastically increases the height. Evening out makes the degrees smaller on average, so taller trees. So the height of T is stochastically smaller than the height of T prime. Okay, so those are the theorems. The key proof technique is a new so I said a new proof of Cayley's formula, but that technique, that proof, which I'll show you in a picture, really specializes to give a tool for coding trees by sequences. Okay, and so that's the work that's with, I said on the title slide, with Serta and Michael Mazoun and James Martin. Okay, but we also use a sort of extension of that work, which I think is important to mention because there's a really clever extension I don't really have time to tell you about, but it's due to Arthur Blanc-Renaudi, who's a doctoral student with Nicolas Broutin in Paris. I don't know if he's actually in the audience, but anyway, he was working on similar ideas in parallel, and we needed some of them for these stochastic relations between tree heights results. Okay, so I'm gonna switch over now in the last 2 minutes, show you the proof technique. So let's see, I guess I want to share this video. Okay, so so what this is going to do, is everyone now seeing a sort of a square? Yes, good. Okay, so we'll start with a tree. So here's a random combinatorial tree. The root is vertex 6, and the leaves are in red. Okay, and now we're going to transform this tree into a sequence. So the tree has 10 vertices. The sequence is going to have 9 entries. And the way we're going to do that is just by listing the non-leaf vertices of the tree in some order with repetitions. And so the rule is this: we start from the root, which is 6, and we look at the path to the smallest labeled leaf, which is 2. And we just record the labels along that path, but we omit the last label, we omit the leaf. Okay, so we write down 6, 1, 4, and then we omit 2. Okay, we started with 2 because it was the smallest labeled leaf. Now we do that again with the smallest labeled leaf that comes next, so that's 5. So the path will start at 4, which is part of the tree we already built, and continue to 5. So the path is 4, 8, 10, and we omit 5. Okay. We keep doing this. We're always drawing the path from whatever tree we've built so far to the next smallest labeled leaf, and then recording that path with the leaf omitted. So the next path is just 4, 7, but we only write down the 4, we omit the 7. Okay, and the last path is 6, 3, 9. We write down 6, 3, and omit the 9. Okay. And you see when you do this, so you end up with this path down below. It always has 1 fewer entries than the number of vertices of the tree. And the repetitions in that path correspond to the times when you started new branches. So they tell you how to reconstruct the tree from the path. Okay, so if we want to go the other way, we look at this path, we follow along until we see a repetition, and we know that that should be a branch of the tree leading to a leaf. And we can tell what leaf label to use because the first branch always went to the smallest labeled leaf, and the leaf labels don't appear in this sequence. So we just, let me back that up a tiny bit. We take the path 6, 1, 4, we see a repetition, 4, okay, so we cut here, and then we attach a leaf, which is just the smallest label, a leaf label, which is the smallest label not appearing in the sequence down below. Okay, so that was the first step. Next, we do the same, 4, 8, 10, we see another repetition 4, Okay, so we make another branch attached using the next smallest available label. And we just keep going like that. Okay, so this is a bijection between rooted trees with vertices 1 up to n, and sequences of integers of length n-1 with entries from 1 up to n. So that tells you there's n to the n-1 such trees, which is Cayley's formula. But it also has the property that the number of repetitions in the sequence of a given integer is precisely the number of children of that vertex in the tree. So it specializes to count combinatorial trees. And really all our analysis sort of hinges on that fact. Okay, I'm 1 minute over time already, so I'll stop there. But thanks very much for your attention. I'm happy to take questions.
So thanks very much, Luigi. So I think people are clapping with muted on, but
that's great.
So, well,
Thank
maybe
you.
We'll do a proper clap later. But so does anyone have any questions? I have a question if no one has an immediate. So maybe
I want to ask a question.
Yeah, go ahead.
So in your first theorem about the stochastically controlling two random tree, those two trees have to have the same number of vertices? Because in your second theorem, they seem to have the same number of vertices.
That's a good question. Yeah. So no, they don't have to have the same number of vertices here. You can use the basically you can make them have the same number of vertices in a sense, but no, they don't have to in this theorem. There's a simple fact, which is that if I just take some tree and start adding path vertices, then the height stochastically increases, because you can do that in distribution just by randomly subdividing edges, and that only makes the height go up. So once you notice that, then sort of you can reduce this theorem to the case of having the same number of vertices fairly straightforward.
Okay, thank you.
Thanks.
So I wanted to ask about your first theorem. You have this condition that you want at least epsilon n of the vertices to be leaves. Do you think that that is like the sort of the weakest possible condition? Like, could you get away with n to the 1 minus something?
No, not quite. I mean, so the point is that you can think about what you really want to do is, if you want to know what's the best you can do, is think about a sub-binary tree with that number of leaves. So, if you have if you take a binary tree with k leaves, and then you start subdividing edges until it has n total vertices, then that gives you a sort of stretch factor for the whole tree. On average, each edge will be subdivided, n over k times or something. So that's so you need to work out from that what the optimal thing is. But no, as soon as I mean, I think this is the right dependence, and it should sort of extend down to sort of a sub-constant proportion of leaves.
So there are a few questions in the chat.
Yes. So let's see. Can you get similar bounds for the width of the tree? So those bounds were known for for sort of trees where the sort of degree distribution has finite variance, the empirical degree distribution, if you like. Once the degrees get large, the width gets larger than square root n, so you wouldn't get the same bounds. Our tools don't give access to the width as readily as they do to the height, in fact. They don't in particular proceed via like an analysis of a breadth first search or a depth first search, where you can quite naturally read off the information about the width. So yeah, I haven't particularly thought about that, but this set of tools doesn't seem to me optimally suited to studying the width. Is there an interesting question you can ask about the proportion of leaves? I'm not sure. I certainly can't on the spot, but I'll think about it. Thanks. So maybe I'll stick around in the break and answer more questions, but maybe we should try to keep on schedule.
There's a question about whether it is the bound is sharp, the upper bound is sharp for some x.
Oh yeah, I mean it's sharp. For finite variance trees, it's sharp. And in fact, we use similar techniques to get bounds that are basically sharp for lots of cases, for infinite variance as well. And trees that look like stable trees in various regimes, we get sharp bounds. The technique seems to be quite good at getting sharp bounds. I didn't state all of our results for time.
Okay, so maybe we should move on, but before we do, if anyone who wants to unmute themselves and give Luigi a round of applause. So Leonid, are you ready to share your?
Yeah. So. Oops. Hope you see this?
Yeah, that's great. Thank you. So our next speaker is Leonid Mytnik, and he's going to talk about limiting behavior of the extremal process of branching Brownian motion. So thank you very much.
Okay, thanks, Sarah. So I'd like to thank the organizers for inviting me to this meeting, and it's a great pleasure to meet many friends. I'm going to talk about the limiting behavior of the extremal process of branching Brownian motion. And this is a joint work with Leonid Mytnik and Jean-Michel Roquejoffre. Okay, so I'm going to talk about branching Brownian motion, and I'm pretty sure that this meeting everybody knows the object, but I just to make it precise, say a few words. So we start with the branching with the Brownian motion at point 0. It goes like this, and the rate 1 it splits into 2. So we're going to talk about binary branching Brownian motion. Then each descendant also at rate 1 splits, and so this way the things go continue. When I talk about branching motion, I talk about Brownian motions with variance 2, which is a bit simpler for notational purposes, but one can take any variance, but we'll take variance 2. Each particle, so we label the particles in the branching Brownian motion. So starting from x1 is the rightmost particle, x2 is the next one, everything at time t, the positions of particles. And the duality relation McGill says that in fact one can get precise distribution for the position of the rightmost particle. So if I ask what's the probability that position of rightmost particle at time t is greater than z, this is function u of time and z, and this u in fact solves the following nonlinear PDE. So derivative in time equals to second derivative in space plus reaction term. This term comes from the Brownian motion, from a motion of particles, and this term comes from the binary branching. And if I start this equation with initial condition, which is a Heaviside function, so functions like this, this function, so then we solve this equation, and this gives in the end the probability that the rightmost particle is greater than z for any z. Okay, so this equation is famous equation which is called after Fisher, Kolmogorov, Petrovsky, Piskunov, and sometimes we call it Fisher KPP, sometimes we call it FKPP, sometimes we call it KPP. All these names we'll use, I may use in this talk. Okay, few words, and this equation plays a very important role in studying branching Brownian motion, and also in this talk. So a few words about Fisher-KPP equation. So here it is. There are so-called traveling wave solution. So which means if there are solution of the type which looks like this. So this is, we always, by the way, take about solution that take values between 0 and 1. And so we can talk about the solutions which go, which have the same shape, and this shape travels to the right with certain speed, and here the speed with it, which it travels to the right is speed 2. It's in fact the minimal possible speed for constructing traveling waves in this for this equation. And this function capital U, which gives a shape for traveling wave solution, solves this this differential equation. And so this function U also is equals to 1 at minus infinity, at 0 at plus infinity. And we also know the rate of decay of the function at plus infinity. It decays as x times e to the minus x. Okay, so these are so-called traveling wave solution, and definitely we may have other solutions to this equation. So we can think about this equation starting from initial conditions which are compactly supported to the right. So if this is exist again 0, 1, and I can take the initial conditions such that, so there is some R0 such that initial condition for F Fisher KPP equation equals to 0 after a certain point. Okay, these are basic initial. If you take this initial condition and ask what's going on with this equation, then it turns out that in fact it converges as time goes to infinity. If we look at particular frame at particular position, then we'll see in the end the traveling wave solution.
Yes, definitely.
Okay. Okay. So let's take MT, which is 2t minus 3/2 logarithm. And it turns out that if I look at the solution to this equation for large times t, so around MT, which is around the 2t with logarithmic correction, then as time goes to infinity, this solution converges to the traveling wave solution, shifted by some value which depends on the initial condition. So I can change initial condition no matter what happens, so it will converge to traveling wave. But for depending on initial condition, it will be shifted a little bit around. Okay, and this guy is called Brownian shift. And using this fact and the McGill duality, one can easily, easily deduce that x1t minus mt is tie sequence of random variables. So in fact, the rightmost particle is one can find around this value mt for large times t. And this brings us to the next question. So, okay, if the rightmost particle, in fact, one can show converges as time goes to infinity, what happens with the whole process of branching Brownian motion if you look at it around, so from the perspective of the point MT? Yeah. So, and what we are doing, we define the process xt, which looks at our process around point MT, and we, again, just for simplicity of notation, we just reverse it. So in the end, what for times, what we see, and by the way, so we characterize our branching Brownian motion as a point process by sum of Dirac measures. We'll put the H Dirac measure at the position of the particle shifted by MT back. And what we see here, we see these positions of the particle in the process xt. Just pay attention that this particle, which is the leftmost particle of the process, in fact, was the rightmost particle in the original process, since we reversed here everything. Otherwise, it's just the same. Okay, this is the leftmost particle in this process, but it was the rightmost particle in the previous one. And since we shifted everything around to MT, so we see that the leftmost particle anyway will be around 0. It will be here, maybe here, but it won't run away. And in these two very important papers, so two groups of probabilists so independently showed that this process, as time goes to infinity, converges to the process x as time goes to infinity, which is again sum of Dirac measures, and they call the limiting process the limiting extremal process of BBM, or decorated Poisson point process, or Poisson process of decorations. I just call it extremal process of BBM. Okay, this is what happens with this guy as time goes to infinity. Okay, and you may ask how one may characterize this process, the limiting one, and just a notation I'll use in this talk. If there is a measure mu and function f, mu of f is integral with respect to mu. And if I take any function psi in this space of non-negative bounded functions compactly supported on the right, so starting from some point at 0 to the right, and I take the Laplace transform of the measure x. So I take any test function, integrate it with respect to this extremal process, and ask what's the Laplace transform. It turns out that this Laplace transform can be written, seen as Laplace transform of another random variable z, where z is the limit of derivative martingales. I don't get into this, but there is a derivative limit of derivative martingale process closely. So again, a very important process for studying branch and Brownian motion. And so we look at the Laplace transform of this z at the point which depends on the shift of certain transform of function psi. So here is function psi. This is psi hat, which is this transform of function psi. And pay attention, this psi hat is take values in 0, 1, always. Okay, since this guy is non-negative. And so this Laplace transform equals to this Laplace transform. It doesn't help us that much, but fortunately, there is a conditional version of this statement, which says the conditional Laplace transform of this measure, given I know the limit of derivative martingale z, is just this expression which we have seen here. And this is now very, very helpful, since it says that if I know z, then this Bramson shift, I remind you, this is the Bramson shift that we introduced a few minutes ago, contains all the information about the distribution of this extremal process of BBM. So if I know how some properties of this Bramson shift, I may translate it into the properties of the distribution of the extremal process. Okay, and the next question we ask, so I remind you, so what is the extremal process? So we see the particles, so this is 0, so we see all these particles, they're here. Now the question we may ask, so if we ask how many particles will be up to this position n on the real line, so how the number of particles increases as n goes to infinity. This question was asked by Cartinius, Hartung, and Louis, and they answered these questions. They showed that the number of particles up to here n, as n goes to infinity, if I normalize this number of particles, but n, en, and z, this will converge to some constant a0. They didn't identify the constant. And another question is, what is the fluctuation of this quantity around the limit? Okay, and we'll address these questions in our work. Okay, so essentially they showed that number of particles. This is the number of particles. So so as n large, so it increases like some constant times z, and times n to the n as n goes to infinity. Okay, this is the behavior. This is how it increases. Okay. So and now this is now from here I state our result, which is a little bit more general in the case. By the way, sometimes we call this law of large numbers, this result, and result about fluctuations central limit. Okay, so we define the measure yn dx like measure xn dx scaled by n e to the n. What is xn? Xn is we take our process x and shift all the particles for any given n. We shift all the particles to the left by n. Okay, so around 0 we'll see all these particles which are around n. And now we take this measure xn, which looks at this at the configuration of these particles. So it's actually around here, but it's shifted to 0. And it's clear that if we get the information about this limiting behavior of this yn, then we recover the continuous Hartmann-Luedor result, and maybe we have a chance to get what is A0. And we also defined mu dx, which is just the exponential measure, so ex dx times some constant. So the first theorem which we have seen, in fact, we can show that this measure yn dx, which we defined here, converges as n goes to infinity to mu dx multiplied by z. Okay, this is the first result. And then one can check himself that y and dx look like exponential function, so shifted by log z to the left. Essentially, it's exponential function. And so theorem 1 immediately gives us that this quantity that in the paper of Cartinius Hartmann-Luedor was studied what is behavior is exactly the limit of this guy is exactly the limit of the mass of the measure yn on the left of the left half of the real line, and we divide everything by z. But since yn converges to measure mu times z, and here we divide by z, the limit of this guy is just mu, the mass, the measure mu of the left half of the real line. Okay, and we get that, and we know that since we here this is the definition of the measure, then we get the measure mu of the half of the real line is 1 over square root of pi, which immediately gives us the constant A0. So we're able to identify this constant A0, which wasn't identified in the previous work. Okay, so again, measure yn, so which concentrated around, so which is somewhere here, and it's increasing, by the way, exponentially, as I say. It's exactly what we need to answer the to recover the result of Cartinius Hartung and Luedor. Now you just remark, we can reformulate theorem 1 as follows. We consider the same measures xn, but additionally we shift them by log z. And similarly, we define yn star. It's the same measure scaled by n e to the n. And then one can get the following version of theorem 1, that this is yn star converges to mu dx. Essentially, we just defined by z our measure in the end. Okay, or shift it, whatever you want, where you want to see it. It's just the same theorem formulated in another way. Okay, so we know that yn star converges to mu, and we know how mu looks like. Yeah, it's explicit measure. And now we'd like to study fluctuations. And so in principle, we will probably expect that we take yn minus mu and somehow rescale it and see what's going on. You would like probably to see yn minus mu and see how this guy behaves as n goes to infinity. It's yn goes to mu. Turns out that it's not the right thing to do. We need to add another correction to our difference, this 2 log n over n factor here. Not just yn minus mu, also need to take minus mu to log n over n. We take this difference and multiply it by n. And it turns out that this is the right guy to consider to study the fluctuations of yn star around its limit. Okay, we can do the same in terms of yn, not necessarily yn star. One remark, so this term appears also in a number of papers of Pascal and Michel Pen, who studied the limiting behavior of the some quantity rate to branching Brownian motion. So we define this signed measure. Yeah, we have this measure minus this measure, and let R be spectrally positive one stable random variable with this Laplace transform. Then the main theorem here in this slide that there exists some deterministic measure mu dx. We can write it explicitly, such that conditionally on Z, this signed measure, this rescaled difference, converges to random variable R times mu dx plus deterministic measure. So essentially, the fluctuations that we see, again, in the limit, they are spectrally positive one stable random variables. Okay, this is the second main result. Okay, and just a few words about the proof. The proof based on the studying the conditional Laplace transform. So we know the conditional Laplace transform, and it's based on studying this Brownian sheet, how it behaves. Essentially, what we want, I just talk about the first theorem of convergence of Yn. So what we want to show? We want to show that Yn converges to mu. This is our goal. Okay. And so let's try to see the behavior of Laplace transform of Yn when we integrate it with respect to some non-negative test function. Okay, so and do it as conditionally on Z. Fortunately, we can always write this Yn integral of phi 0 with respect to Yn as an integral of another properly rescaled phi 0, which will be phi n, integrated with respect to x. And this gives us this, and now we use this conditional Laplace transform formula for the extremal process of branching Brownian motion, and we get this. And now you see, so we have here z, and we have e to the minus Brownian shift, and here function psi n, where psi n is 1 minus e minus phi n. But what is phi n? Phi n is our shifted function phi 0. We shifted by n, and rescaled by n e to the n, which means phi n is extremely small. Yeah, as n goes to infinity, phi n is very small. So our goal is to study the limiting behavior of Brownian shift for very small initial conditions of the Fisher-KPP equation. If we can see how the Brownian shift depends on very small initial conditions of the Fisher-KPP equation, we can get the answer. And if you get that this guy goes to mu of phi 0, we're done. Okay, this is more or less this very simple idea. And here the main tool that we use for our proof is this theorem, which says the following: fix any phi 0, any function which is non-negative with compact support to the right, so function which looks like this. Okay, so there is so it has compact support. This is phi 0. Multiply it by epsilon. So we have Brownian shift of very small initial data, some function phi 0 multiplied by epsilon, and we're able to identify the asymptotic of this Brownian shift dependent on epsilon. And here there is a number of terms. There is several terms that don't depend on phi not at all. this log epsilon minus 1, so which means this shift is huge. Some log correction, some first order term where you see by the way the mu of f0. Okay, another term, and this is the lower order term. One remark: these three terms we need for the law of large numbers, and all of them we need for the fluctuation. But for law of large numbers, these three are enough. If you know this, and we take here in the previous slide epsilon to be n minus 1 e minus n, exactly what we see here. This is epsilon. Use this asymptotics, substitute it here, then you immediately get that this guy will converge to mu of phi 0. It's just a few seconds, few minutes of calculations. Okay, very simple algebra. Okay, since you see the mu of phi 0 here, eventually it will appear as a limit. And this immediately gives us that, in fact, yn phi naught converges to mu phi naught as n goes to infinity. And the similar idea, so when you study fluctuation, you just need to use all these terms for getting the limit. And this somehow how the proof goes. Proofs uses the results on the Fisher KPP equation to show the behavior of the extremal process branch Brownian motion. Doesn't use the probabilistic structure. We don't need to know. We don't use the probabilistic structure of branching Brownian motion to show this result. Just the behavior of this Fisher, the Bramson Schrift, which in fact encodes everything that we need to show the convergence of the quantities we study. So thank you for your attention.
Thanks very much. So does anyone have a question before we go to the coffee break? I have a question if no one wants to jump in. So I have a question about your how you get these asymptotics of the shift. So you said that you didn't use the McGill connection to the BBM, but do you use a Feynman-Katz formula, or is it a purely PDE proof?
It's a pure PDE method. Yeah, pure PDE method studying this studying the asymptotic of the shift. So in fact, so we know that this shift appears from the long time behavior of the Fisher KPP in the end. So you start with the Fisher KPP and carefully study its long time behavior, and you see the shift. So these three terms, they're I don't say easy, but it's the easier than getting this correction. This correction is a nightmare. But you need to get up to here to get the CLT theorem. And so this was really hard work. Up to this, you kind of believe, and this, in fact, this you can prove it without PG if you use the morally without PG if you use just the law of large numbers that Cartesius, Hartung, and Luidor proved. In fact, this you understand that this should be the expansion up to here, but up to here, so it's already much more difficult.
Yeah.
Can I ask something about this expansion, Leonid?
Yeah.
So, I mean, one way to read this is that this looks a little bit like the Bramson expansion, or the Van Salos expansion, if you replace time by log epsilon minus 1, right? So you have the linear term, which is a log epsilon minus 1. Then you have a log correction. Then you have a constant, which depends on the initial condition. And then the next term is indeed log t over t, right?
Correct.
And then, but then I would expect to see, something a 1 over root t, or.
Yes, but you see exactly this. But you see now, you see 1 over t. That's what you see.
So
and
why
this,
not?
And this guy, in fact, that the one that gives you one stable distribution. This guy. So I don't write what is C1 of phi 0, but this is exactly where the one stable population is hidden.
But
And
you're missing a term between the constant and even the log t over t, right? The 1 over root t I would expect to see before. That's why I'm
yes,
surprised not to see that.
No, we don't see this. No.
That's interesting. Okay.
Yeah. All right. I believe it's similar to in many respects. And so we talked with Pascal. It's somehow, but he studies this time asymptotics of things, and this time, this similar things appear there.
Yeah, absolutely. Okay, thanks.
So are there any other quick questions? Perhaps if not, we should unmute ourselves and thank Leonid for his very nice talk.
Yeah.
So now we have a 15-minute coffee break, and then we'll be back for Christina Goldschmidt's talk. So I guess feel free to stay in the Zoom room if you'd like, but we can go back to Gather Town and wander around.
Right. So I think you can just stay in the Zoom room, but switch off mic and camera and go back to the Gather Town room. All right. See you there.